So what we've done then is we found the displacement using velocity times a time interval. Okay, so we took an average velocity in the time interval and the time interval. We multiply those together to get the displacement. So what's another way we can get net displacement from a velocity function? Well, if velocity times time equals displacement, and if you recall that our model for multiplication is area, length times width equals area. Okay, so if we take a look at velocity times time, we can actually look at it geometrically and see that velocity is actually the vertical axis, time is the horizontal axis. Well, that is length and width. And we can work out the velocity using our area model. So if we say that this is a velocity function, if we take a look at this is a constant velocity of 5 meters per second. Okay? And it's going at 5 meters per second for, looks like 10 seconds. So if we were to take 5 meters per second and along the x-axis we take 10 seconds. If we multiply those together, we're going to get this area here. And the area is going to be 5 times 10 is 50. And if we actually work out the units, meters per second times seconds gives us meters. And it's pretty hard to argue that if you're traveling at a constant velocity of 5 meters per second for 10 seconds, that you didn't travel 50 meters. We did. Okay, we've gone 50 meters, and that area of 50 meters is our displacement. Okay, and again, length times width, velocity times time is going to give us displacement. And so the area under that velocity function is the actual net displacement. We moved positive 50 meters in that time interval. Now, this is slightly different in that the velocity is changing, right? But if we take the velocity times time, 2 meters per second times 2 seconds, well, we know that's 4 meters of displacement. That area represents 4 meters of displacement. Now, if this area is the displacement, well, although this is not constant velocity, if I look at the shape of this, I could say that this is a trapezoid shape, and I do know how to calculate the area of a trapezoid. Okay, so what I can do is I can say that between 10 seconds, 0 seconds and 10 seconds, my average velocity, so here's 2 meters, I'm starting at 2 meters per second, and it's increasing constantly at a constant rate. I end up at 10 meters per second, and I can actually take the average velocity of 6 meters per second, so take that space there, and I can just kind of use that as my area. That's how we calculate areas of trapezoids. We just take the average height of the trapezoid and multiply it by the width of that trapezoid. And you can see that rectangle here is going to have the same area as our trapezoid. So this area of the trapezoid is going to be 10 meters per second plus 2 meters per second, okay, divided by 2. And then we're going to multiply that by 10 seconds. Okay, and when we do that, we end up with a displacement of 60 meters. So what I've done is I've found the area underneath this trapezoid, okay, and I'm going to claim that area is 60 meters of displacement based on this increasing velocity situation. Now, if we take a look at the area here and the area here, yeah, this trapezoid area, yeah, we're probably going to be about 60 meters. Yeah, that seems to make sense. If we start at 2 meters per second and end up at 10 meters per second, we're traveling slightly faster than, on average, than this situation on the left. And for the same amount of time, it looks like we traveled just a little bit further using this accelerating situation where the velocity is changing, or in other words, we're accelerating. Okay, so this is how we're going to find the velocity of these the displacement when the velocity is changing. We're just going to kind of take these, find this area under this curve and say that that's going to be our displacement. Okay, so let's try this then. So here we have, again, here's my velocity. Velocity is now changing randomly, but we can still just say, well, we can estimate the net displacement in that interval by just saying this. We're going to, in the first second of time, we're going to say that the average velocity here is going to be 6.5 meters per second. And so for 1 second at 6.5 meters per second, we're going to say that the displacement is 6.5 meters. From here to here, our average velocity is going to be 6 meters, and that's over a time interval of 1 second. So we're going to say the displacement here is going to be 6 meters. So we can use the velocity times time to find our displacement. And although our velocity is changing, what we're going to do is we're going to just estimate the displacement by using the average velocity. So here in this interval from 2 seconds to 3 seconds, we started at 4 meters per second. We ended up at 7 meters per second. So the average is 5.5 meters per second. And that's over 1 second. Here the speed stays constant. So we're going to say that they traveled 7 meters in that 1 second. And here we're going to say that they traveled 8 meters in the last second. So this is our displacement, and we can find the total net displacement by just adding those up. So the total net displacement, I'm going to get 12.5, that's going to be 18 meters, 25, so it looks like 33 meters of net displacement. Okay, so this is a good way to do it. Now, if this was constantly accelerated, give us a nice shape like this, we could say that that's exactly 33, but the problem is we don't actually know how this velocity is changing. Okay, so this is really just an estimate because we don't know that we went from a velocity, velocity of 5 meters per second to 8 meters per second in a nice smooth acceleration. It could have gone down, and we could have gone like this. We don't really know. And that the areas under the curve, which would represent the displacement, area under the velocity curve, which represents displacement, could vary depending on how that curve is shaped between the 2 points. Okay, so that's why we have to consider that an estimate and not the exact displacement.